Hey everyone, my name is Tovio Roberts, and there I am. My name is Tovio Roberts, and this is Galvanize DSI Prep Study Hall. Feel free to post questions in the Slack, and when I don't see questions in, I'll do some exploratory coding, something like that. Happy to answer questions for, concerning places where you might be stuck in the Python or the stats materials in our basic prep or premium prep for that matter. So it looks like we have a question already. Let's look at this. So having trouble with dictionaries, problem 2. So I'll pull this up and I'll show you where this is in our materials. So problem 2. We have it here. Write a function called reverse dictionary that takes in one dictionary as a parameter and will return a new dictionary that is the reverse version of the passed-in dictionary. By reversed, we mean that the keys of the past dictionary become the values of the new dictionary, and the values of the past dictionary become the keys to the new dictionary. Okay, so this is one of those kind of classically Python problems, really. Let's kind of walk through how you might go about doing this. Are there any? Nope, there are no examples that we can use, but we'll just make a dictionary and work on that as the example. Okay, so let's say we have some dictionary, and that dictionary is, let's call it D, and I'll just make this a little bit bigger. Do that. So D is going to be composed of some elements, and let's say we have, well, this is interesting because we want, there isn't any extra text in here saying what we should do if there is a duplicate value. So I think what we're going to assume is that there are no duplicate values. Okay, so let's say we have some pets. We have a cat, where we have 2 cats, and we have, 3 dogs, and we have 20 squirrels, like that. Okay. So what we want to create here is a dictionary where the keys are these numbers, right? The number 2, and that will correspond with cat. The number 3 should correspond with dog, and the number 20 should correspond with squirrel. So let's think about how to write that. This is going to be called reverse dictionary, and we'll pass in a dictionary, which I'm just calling DCT. So what we can do, we can just make another dictionary, like make some collector. So maybe I'll call this outD, and I'll initialize it. It'll be an empty dictionary as we're seeing it. And I can say, well, I can just reverse that initial dictionary, right? So for the key and the value in dct.items, I have to use .items in order to access all those entries, the key value pairs, as tuples. Those will unpack into key and value. I can just take this out dictionary sub key and attach to that, sub value, and attach to that the key, like that. So this is going to get us kind of the inverted dictionary, which we can return like so. So we've got D here. Let's just make sure this is working okay. What is this called? Reverse dict. And we'll pass in D, and let's look at the output. So I think we know what we should expect here, right? We should expect 2 cat, 3 dog, and 20 squirrel. And that's what we get. 2 cat, 3 dog, 20 squirrel. Let me just make sure this works in case I missed something. But I think that should probably work. So that is, right, that's challenge 2. Yep, and it looks like that passed all the tests and it's fine. Cool. Yeah, and I think you know, there are other ways to do this, but this is pretty easy in the sense that you're just making a collector, right? And you pack in a dictionary in the same way that you always do. You just you know, traverse whatever you're going to pack in as the key values, and then you just do that. So on the technical interview, right, we focus quite a lot on dictionaries, and dictionaries are I think of them as being the most complex data type and most maybe flexible data type in base Python, right? You can do kind of a lot with it. When you get past the technical interview, you know, you kind of switch gears toward pandas data frames, which are more like they're sort of akin to Excel tables, but you get a lot of very functional methods, and you can do really excellent procedural code, which is quite a bit harder to do with Excel. But yeah, so that is that. Let's see. Any other questions offhand? If you have them, go ahead and post them in. Otherwise, I might pre-game the premium prep tonight and talk a little bit about the binomial distribution. So if you have a question, go ahead and post it, and otherwise I'll move toward binomial. Okay, cool. So let's think about the binomial distribution. And the way that I usually teach binomial is from kind of a ground, you know, like what I think of as first principles when it comes to binomial. So let's think about what binomial is, just starting off with. So we've got binomial. I'll say explicitly this is the binomial distribution. It's a discrete distribution. What do we mean by discrete? Let's just consider the values in it are countable, and we'll see why that is in a second. So when we're thinking about binomial, this is rooted in a Bernoulli trial, okay? So maybe let's think about what a Bernoulli trial is first. So a Bernoulli trial is sort of like a coin flip, right? Let's think about it like it's a coin flip. And if it's coin flip, then the probability is 0.5, right, for a fair coin. And so Bernoulli is either going to come up, well, for a coin flip, it's either going to be heads or tails, right? It'll either be heads or tails. And that's fine. Those are the two options we have. But we can sort of abstract away from that, and we can think about this as success or failure, right? Where we're thinking about heads as being success, tails as failure, but we could switch that around. We could think of tails as success and heads as failure. It doesn't really matter. We define what is success and what is failure. So if we're thinking about the idea of success or failure, we can take that a step further, and we can call this true or false, right? Where true represents success and false represents failure. Or we can take it a step further, which I'm going to do, and say 1 is success and 0 is false. So that's a Bernoulli trial. It's a single trial, right? It's a single flip of a coin. Although be careful, because we can vary this value of p. We can change p from 0.5 to 0.8, and then we're asking, you know, what is the probability of getting, you know, if the probability of success is 0.8, what is the probability of success? Well, it's 0.8. This is sort of, I don't know, Bernoulli feels a little like a tautology in some way, but it does help us construct other distributions really, really well. So binomial is rooted in Bernoulli, and sometimes binomial is even called a Bernoulli process, although that same term, that same phrase, we can think about it as binomial process, right? Binomial process, Bernoulli process, it's kind of the same thing. What does that mean? It means that binomial is a series of Bernoulli trials. And what we're interested in is the number of successes, which we call k. So it's k successes in n trials, right? If, with that in mind, we also have another parameter to the distribution that is p, where p is the probability of success on any given trial. And just notice that this is going to change. This is not going to change across all the trials. So the probability of success is a constant across all trials, Bernoulli trials in a binomial process. A tautology, as I mean it, is that the meaning is sort of inherent. Bernoulli is kind of like, I don't know, or the tautology that I was expressing was, well, what's the probability, if you have a Bernoulli trial with a probability of success of 0.5, what's the probability of success? It's 0.5. In that way, Bernoulli is sort of like, it's self-descriptive in some way, and we get out of it exactly what we get out of it. But it does help us construct other distributions like binomial. From binomial, we extrapolate Poisson. Bernoulli also helps us when looking at geometric. So that's what I mean by tautology. So a binomial distribution we can think of as a series of Bernoulli trials where we are interested in k successes in n trials, where p is the probability of success. So another question just came in. So I'll put this on pause for a minute, and I'll put binomial on pause, and let's look at this question. Okay, so we're looking at under string functions and methods, lower upper capitalize, which is, and we're looking at question 3. So let me just pull this up and take a look at it. So write a function called string up. This function takes 2 arguments. The first one, called string, is a string on which an operation can be performed. I know this is really tiny, isn't it? The second one, called command, can be any variation of the words upper, lower, and capitalize. For example, upper could be spelled, U, capital P, E, capital R. This function should return a new string that is the result of the command. If the command isn't valid, return invalid command. Okay, so I think we're just returning. I see. All right. So upper here is an indicator that we're going to use the .upper method. That's what we're going to apply to the string we pass in. The string operation that we're going to perform is upper, and we're going to perform it on this string. Okay, and here's our output. This is an example. I think this is pretty straightforward. So let's grab this. And yeah, let's go ahead and work through this. So if we call string up, we should expect to see that result. So let's do not Python. Let's do def string up, and we're going to pass in a string. That's our parameter, and we're going to pass in an operation. I'm not sure if that was the way that was done. Is that what that? We're calling it command. I'm sorry. So not operation, but we'll call it command. Okay. So let's look at this. There are a few different options that we have here. The variations of the words upper, lower, and capitalize. And I'll just paste these in for the sake of having them here. So we're going to see these variations, upper, lower, and capitalize. Okay, so the first thing I'm going to do is I want to look at this command. Now, notice that the command can have any combination of upper and lowercase letters. It just needs to have the word upper in there. So how do we make this look like this? That's pretty straightforward. We can say if command is, actually let's do command.lower. If command.lower is upper, then we're going to do something. So that's one of the instances. And I'll just grab these. If the command.lower is lower, if the command.lower is capitalized. Okay, so this is on our way. We're kind of scaffolding what we want here. I'm going to make these into elifs. And we're going to have an else in there as well. So what is our else? Our else is going to be, I'll copy that in as well. Remember, copy paste is your friend. I'll copy in the return of invalid command. Okay, so I've got all these errors showing. It's because I'm not doing anything. I can do this in a couple of different ways. Now, the string operation that we want to perform is, is just these names, right? So if that's the case, I should just be able to return string.upper or string.lower or string.capitalize. And I think that should probably work. There might be something I'm missing, but let's find out. So we're getting all caps. This is an example. I should put in other versions of this just to check. So there's .lower. That's working. And then capitalize. That's working. Yeah, I think that's it. So let me see if that actually passes the tests. I think it will, but can't be sure offhand without actually passing it in. Yep, so that passed tests on my end. Again, all we're doing here is checking the command .lower, and if that matches upper, lower, capitalize, or upper, lower, or capitalize, then we just perform those specific operations to the string, and in the other condition, if it's none of those words, then we return invalid command. So just clear that. All right. So back to binomial. So this bracket notation, I'm using this a little bit informally. The reason I'm using it is I think about this. I think about traversing this in order to count in a series of for loops. But I have seen this represented this way, a 1 or 0 in relation to Bernoulli. I've also seen it represented as a set. Here's the set of possible outcomes for a Bernoulli trial. So curly braces or square brackets. I've seen both, and that's really it. So there's a question on that last one. What am I doing to pass tests? Well, I'm not doing anything, I guess I'm not doing anything specific to pass tests, but let's just play around with this a little bit. We can see the test results, but we're not seeing any output from the test results. There's no real feedback here aside from it's good or it might not be good. But let's check this. If I change upper right here to lower, then my assumption is that we're going to fail the tests. We're going to fail at least one test. So failure is 1. And we can see that what we should have seen is, this is pretty hard to read, and what we got is, we should have seen that in all caps, but we got it in all lowercase. Now, if you think about this as being kind of a step-by-step operation, it looks like our first test is checking upper, and then we're sort of failing after that. Why don't I change this one to upper as well, and let's see if we pass at least one test. Okay, so there's something happening here where, well, what I think is happening here is that we're really just failing one test at a time, and it's showing us that. So where are the tests located? Those are located behind, they're located in a GitHub repo where we have the formal test worked out there, and we don't expose those tests, we don't share them, because there are times where our tests are essentially, our test includes the solution sometimes, because sometimes that is a, that's not a good testing practice in the, like, a software development industry necessarily, but if we're testing against, the viability of someone's function, then we might just put a working function in our test and then, compare output between the two. Like, this is what it should be, and this is what it is. So we don't expose our tests. In most of these cases, we give, or in a lot of these cases, we give an example, like this example, where here's the input and here's our expected output. And in general, when you write a test, you kind of do that. It's like, well, what do you want your output to look like? And you set up an assertion to make sure that the output looks like the assertion. But for us, it can be a little bit easier since we're testing on sort of toy problems a lot of the time. So we might just put a solution in the test itself. Okay, so back to the binomial distribution. It's discrete. It's rooted in a series of Bernoulli trials. That's what it is. It's a series of Bernoulli trials where we are looking at the number of successes, k, which we describe as k, in n trials, and there's a fixed probability of success. So with that in mind, let's consider the probability mass function for the binomial distribution. So we have this concept of the PMF, which stands for probability mass function. And what the probability mass function does is, in general, a probability mass function is going to give us the probability of a specific outcome, right? And the way we might think about this in terms of binomial is, let's say you flip a coin 10 times. What is, and this is a fair coin, what is the probability you get 7 heads, right? So if we're thinking about this function, what this is going to look like is, well, the probability that x, let's do it like this. The PMF might look like this. The probability in a binomial distribution that where n is 10, k is 7, and p is 0.5. These are the three parameters for our binomial distribution. So there's a formula, a very convenient formula for this, and the way that we will often represent this is the probability that x is k. K is the number of successes that we're trying to consider. We could put the other, the others in here as well. So we've got k, we've got n, and we've got p. So let's just think of those as being also entered into your function as parameters. We're going to do n choose k. So notice this is combinations. And we're going to say p to the k multiplied by 1 minus p to the n minus k. This construct right here, this comes up a lot in a lot of other formulas, right? The probability multiplied by the complement of the probability, either with or without exponentiation, depending on where you see that. Now, why do we have combinations in here? Well, combinations because we are counting, we're considering the number of occurrences where we have 5 successes or 6 successes. I don't remember exactly what I wrote. It was, I think it was 7, right? Where x is 7, n is 10, p is 0.5. And we can work through this whole thing. It might be helpful, since we have combinations within this, it might be helpful to actually have the combinations formula in here as well. So let's put that in here. And that's just n factorial over n minus k factorial multiplied by k factorial. So if we have all of this, we can just plug numbers in, really. N is 10, so 10 factorial over 10 minus 7 factorial multiplied by 7 factorial. And this is going to be multiplied by 0.5 to the 7th power multiplied by 1 minus 0.5, which is 0.5, right? 1 minus 0.5 to the 10 minus 7, which is 3. Okay, so I could work through all this by hand, but I'll just pull up a Python terminal to do so, because it'll be a little bit nicer to do that. You know what? I'll just code it out because it'll end up taking me less time, I think. So let's code factorial because we'll need that. I think it's always good practice. Anyone should know how to code factorial offhand. I think that's very helpful. It's a good pattern to know. So here's factorial, where we pass in n. We're going to build up a product, and for a number in range, we're going to start at 1 and go to n plus 1. Of course, we could start at 2, because anything times 1 is just itself anyway. And we can say prod times gets the num return prod. So if I run this, if I print the factorial of 5, that should be 120. 5 times 4 is 20, times 3 is 60, times 2 is 120. And that's what we get. Okay. And then we'll need combinations. So here's our combinations formula, n choose k, and we're just going to take the factorial of n, just like we saw in the way I wrote it out, and this is over the factorial of n minus k multiplied by the factorial of k. Because this is a count, I'm going to just make this an integer, and I'll return that integer. So if we're going to code the binomial PMF, we really just need that formula, right? And so let me snag that formula. We'll translate this directly into Python, and that's going to be pretty easy. So that is going to be the binomial PMF, right? Binomial PMF. And we pass in n, k, and a probability of 0.5. And we're going to return combinations and choose k, right? We've got that function above, multiplied by p to the k, multiplied by 1 minus p to the n minus k. And so now that we have this, we can answer that question. Oops. We can answer that question that I posed above, where we've got n is 10, k is 7, and probability is 0.5. So in 10 flips of a fair coin, what is the probability of getting 7 heads? Let's find out. 0.117. Okay. It's, you know, not really unlikely, but it's not very likely, right? It's we might consider this in relation to a k of 6. What's the probability of getting 6 heads in 10 coin flips? It's slightly more, right? It's 0.205. And then what is the probability of getting 5 in 10 coin flips? That's even higher. Well, is it going to get even higher if we go further down? Let's set a k of 4. Okay, that goes back down. So it looks like the most probable outcome is 5 heads in 10 coin flips. Now, why is that? Well, the way that I like to think about it is that there are more permutations of heads and tails in 10 flips where the heads add up to 5, right? And it's kind of equally balanced if you know, if we get 5 heads or 5 tails, if we have a probability of 0.5. So you know, on every given trial, it's a 50-50 chance of either. There's something kind of intuitive about that our most likely outcome is going to be 5 heads in 10 flips. And then in this case, because it's 0.5, we get this sort of symmetric distribution. If we were to map this whole thing out, we could. In fact, why don't I do that? I'll say for k in range, and we'll go from 0 to 10. We'll include 10 because it's of length 10. And we can just print this k as k. So let's see what that is. And oh, you know what? Let's do this. Let's do k, and I'm gonna do this a little bit sloppily instead of doing an F string, but I think it'll be fine. And now we'll get a representation of the binomial distribution for 10 flips of a coin, of a fair coin. Okay, and we can see that, I think, pretty clearly. It is symmetrical, right? The probability of getting 0 heads or 10 heads is the same. The probability of getting 4 heads or 6 heads is the same. And obviously our most likely outcome is 5. So, you know, at this stage, in a lot of cases, we might ask you to pack this into a dictionary. That's fairly easy. So let's build a binomial dictionary. I'll just adapt this statement directly. So we'll build a dictionary like so, and I'll say d sub k is going to get the binomial PMF of n. Oh, you know, let's put some parameters in here. Let's say n, k, and p. And so when I call this, we'll have something that's a little more flexible. So we'll get k and p, and so I'll say for k, v in binomial dictionary, where we pass in 10. Oh, we don't need k, I'm sorry. Let's just go to n plus 1, and that should work. Okay, so just 10 and our p of 0.5. So let's see what that is. Oh, what am I missing? Oh, I see. I didn't actually finish writing what I meant to write. And this time I will do an F string. I'll just do K and V. None type has no items attributes. Huh. Oh, I'm not returning the dictionary. I'm sorry. There we go. Okay. And here we get that same output that we saw before, but now we have a function that's slightly more flexible, and we can put in different values, right? We could do, I don't know, let's do 0 to, well, let's do 100 trials, and we're wondering, yeah, so we can think about this as 100 coin flips of a fair coin, and we're still going to see symmetry, and this time that symmetry will be around 50. So 50 is our expectation, and we can see that it is a higher number, but notice it's not very much higher anymore than 49 or 52, or at least relative to the how much higher 5 was in relation to 4 and 6. 50 is much less different than its relation between 49 and 51. I think that's a nice thing to notice. So I'm just going to drop this code in the Slack before we move forward. Okay. So there's a question, what does command.lower evaluate to, and why is it used 3 times instead of once? Okay. I think I can back up and we can take a look at that. Let's back up really far. So command.lower, the reason we're using that is the second parameter of the string op function is, it's meant to be a command, but it's messed up. And we want to make it canonical, or some single version of it that we can interpret. And so that's why we're calling .lower on command. It's to make it match something specific. Because if we didn't do that, well, we're not going to match, well, in this case, capitalize is not going to match this capitalize where we have a lowercase a in that point. Those will not match. And so we can use lower here to make it a single version that is comparable. And I think that's really the point of command.lower. And, you know, it just evaluates to a version of command that is all lowercase. That's all it does. Okay, why are we switching what we're looking for in the solution for number 2? It's, oh, okay. Sorry, this isn't in reference to a different problem. This is a new question. Okay, so we're considering probability mass functions, and the question is, let's look at number 2. Okay, so the first question is, given a group of 5 potential blood donors, 2 donors are known to be universal donors. They have O plus typed blood. 5 blood samples, 1 from each individual, have been taken, and the blood type will be tested in random order until the first universal donor is found. Let the random variable x represent the number of typings necessary to identify a universal donor. I'm not sure. Let's just work through both these problems. I think that might make sense, just so that we're not, just so when we get to the specific question, it's clear what we're talking about, or it's clear to me what we're talking about. Why did that change? The question is only asking about one type of outcome. So the switch, oh, okay. I think I understand the question here. Yeah, that is a good question. I mean, I think part of why we're doing that is we're trying to introduce the cumulative distribution function. Honestly, I think that's what's happening there. And the cumulative distribution function, of course, is going to go from 0 up until a number, but we can think about accumulating more than one PMF value, and I think that's why we're doing that there. That's my assumption. So let's shoot, which one? Okay, so 1. So yeah, I think just working through these might be a good idea, just to make it clear. All right, so in this first one, let me grab this as well. So given a group of 5 potential blood donors, 2 donors are known to be universal donors. They have O plus type blood, 5 blood samples. 1 from each individual have been taken, and the blood type will be tested in random order until the first universal donor is found. Let the random variable x represent the number of typings necessary to identify a universal donor. First, find the PMF for the random variable x, then calculate the probability that it will take fewer than 3 blood draws to encounter the first universal donor. Okay. All right, so on that first draw, right, the way we want to maybe think about this is the probability of getting the draw on the first draw. So the probability for let's just say x, random variable x, is going to be related to draw 1. This to me is well, that's 2 out of 5 people, right? So 2 out of 5 people. And now the next thing we want to consider is if we don't get this on the first draw, right, we want to consider x being draw 2. Then we're going to think about this as well, we want to consider that we did not get it on the first draw, right? And that kind of matters. And so, on that first test, there are 5 outcomes, and 2 of them are universal donors. So we want to make sure we don't, we're not getting a universal donor on the first draw. And so we need to consider that because of that, there was a 3 out of 5 probability that we didn't get it on the first draw, leaving a 2 out of 4 probability that we'll get it on a second draw, and then we can just multiply these 2 together, right? So that's our multiplication rule. And then we can take this further, and we can answer the question after this one. So, because I think that's what we're looking for. It will take fewer than 3 blood draws. Oh, well, in that case, that's just going to be 2 out of 5, which is 0.4, right? 0.4. And 3 out of 5 times, oh, I should just be able to do that in my head, but I'm afraid I can't. Let me just do this. So let's do 3 out of 5 multiplied by 2 out of 4, and that is going to be 0.3, right? Okay, and then so if we're looking at less than 3 blood draws, that's either 1 draw or 2 draws. So that's just going to be 0.4 plus 0.3, right? Which is 0.7. So the probability of getting a universal donor within the first two draws is 0.7. So I think that satisfies the first question. And then we ask, given the above PMF, what is the probability that it will take between 2 or 3 blood tests to find the universal donor? Okay, well, in that case, we need this. We need this third round. So the probability that that we get the donor on draw 3. This is going to be, well, we didn't get it on the first draw, and we didn't get it on the second draw, and so there are 2 out of 3 remaining, right? Where, you know, this at this point in draw 3, if we're going to get it on the third draw, there's a 2/3 probability if we missed on the first 2 draws. So let's let me just plug that into a calculator. What's that? 3/5, 2/4, and 2/3. So 0.199 repeating forever is what that looks like. I'm assuming we can just round that to 0.2. Oh, is that wrong? Oh, of course it's wrong. That makes sense. So this is 0.2. But 0.2 is not the answer because we're looking at between 2 or 3 draws, so this is 0.3 plus 0.2. So 0.3 plus 0.2 is going to be the probability that X happens on draw 2 or X happens on draw 3. So let me make sure that I didn't do something wrong. Let's make sure that, oh, yep, that's it. Okay. Is there a way to write this PMF as a formula, or do you have to calculate each stop of the PMF manually? Well, what I see is this is formulaic in some way, and I'm trying to think of a good way to make this formula. So let's work this out one further. By the time we get to draw 4, we should have an answer, right? Does that make sense? We should have an answer by draw 4 because there's 2 out of 2 remaining. So we've got, oh, I don't know why I can't. Oh, because I know why. There we go. So that's 3/5 times 2/4 times 2/3 times 2/2, right? So trying to think of a good way to think about this. I think we could represent this with a formula. I mean, we definitely have this descending series, right? So each, so we're multiplying, and we've got, you know, the number here, and this is, so we could say I is 5 down to 0, sorry, down to what would be a good representation? Down to the number of items we're looking for. So I'll just call that, I'll call it T for target. So I is 5 down to T. So 5, 4, 3, 2 is how many times that should happen. And on our first pass, that should be let's see. I would probably just do this. T over 5 times, you know, I is 4, and then we can say I is 4 to t minus 1, and that could be t minus 1. So I think you could represent it like that. But yeah, I think for this problem, I would just work it out for each one. I think it's a little bit more straightforward to work it out for each one. That's my take on it. I don't think I would try to figure out this formula personally, although I think this formula would be fine. And then you could vary your, you could vary this base, right? The number of items in question, and you could vary t, and that would work. I think that would work. If there's something wrong with this, if you see something wrong with this, let me know. But I think that would actually work. Okay. How am I getting 3 over 5 times 2 over 4? Yeah, let's talk about that for a second. So if we're going to get a success on the first draw, there's 2 out of 5 possibilities that we got the right one, right? That we got a universal donor. That becomes 3 out of 5 because we have to consider the probability of having not gotten the correct one on the first draw, which is, you know, having not gotten the first one on the first draw, which is 3 out of 5. And then we're considering, well, there's a 2 out of 4 probability of getting it on the second draw. Does that make sense? Oh, and this I is 4, that's because I abstracted out this t over 5 items because of this first one. And so if I think that should still work for, I'm sorry, this equation is describing the phenomenon, but it's actually describing this for the maximum number of draws, so this should always work out to 1. It would be better to write a function that does this instead of this statement, which doesn't really match every one of these instances. It only matches the last one. Yeah, I would say just scrap this, looking at it again. But the main thing, I think the main thing that makes this kind of problem difficult is this, right? So here's the probability of getting it on the first draw, but if you didn't get it on the first draw, what was the probability of that? It was the complement. And so that's 3 out of 5. And then you're considering the probability of the second draw. So, yeah, and then this is going to stay consistent, this 2 out of 4, as you go forward. I find these kinds of problems to be, what are you drawing? You are, well, in this problem, you're drawing blood, but you've got 5 people, 2 of whom are universal donors. And so you're hoping to find the universal donor. You don't know which 2. And so if you are looking at the probability of getting the universal donor on the first draw, that's going to be 2 out of 5. And then on the second draw, it's going to be 3 out of 5 multiplied by 2 out of 4, because you already drew 1, right? So there's only 4 to choose from left, but 2 of them are going to be universal donors. So yeah, complement cycling, thinking about complement cycling as a general process. I have to think about that. I think with these, I'll tend to kind of procedurally go through the way I just did to solve them. But there are more general approaches. If you get a chance, there's a book, I referenced this book in class last night. I referenced this book last night called Sheldon Ross's A First Course in Probability, and there are more generalized forms of PMFs in there. And I think and that don't apply to a specific distribution necessarily. I think that's a good reference. If you Google that and just put Sheldon Ross, in fact I'll do that right now. A first course in probability. The first thing that comes up is a link to that book, and I like it. I think it's a good book. I think especially the earlier problems, the problems in the first chapter that lay the foundations for probability are really well constructed. I think they're really fun. Target T and I, and what is it? Okay, to answer your question, let's think about this a little bit differently. Let's think about the kind of problem or the type of mathematical representation we might be using. So this is the summation symbol, right? The symbol I used before was a product symbol, which looks like this. So often in a summation, what we're going to do is let's do a very simple form of this where we've got A. A is a list of numbers, and we'll just say this is 1, 2, 3, 4, and 5. If we're summing these, we're going to start at I is 1, and what we're thinking about here is this is A sub 1, this is A sub 2, A sub 3, A sub 4, A sub 5. Notice that in this mathematical representation, this is using 1-based indexing, not Python's 0-based indexing. There are a lot of really good reasons to use 1-based indexing, and so you do in some languages like R and MATLAB. There are a lot of really good reasons to use 0-based indexing, which is what I prefer in general, and you see that in most programming languages. So I is 1, let's go up to n. N is the length of A. If we want to sum all of these items, we can just do A sub I. So we're starting at 1, and we're taking it up to n, where n is 5, right? N is 5 because there are these 5 items. And we've got A1, A2, A3, A sub 4, A sub 5. And what this works out to is 1 plus 2 plus 3 plus 4 plus 5. If we were to replace this, say, with a summation symbol, which would look something like that, this would be 1 times 2 times 3 times 4 times 5. So I, in this case, is just kind of the iterant, the number that were given by the iterator. How would you represent these symbols in Slack? The way I would do it, personally, is, well, let's think about this. How do I generally do this? I think I do this. I think I say sum, and I say A sub I. Sorry, I would do this. Sum of I is, starts at 1 and goes to n, and I would do something like this, A sub I. Now, is that readable? If you know what it is, it is. But I think another way to think about this, and maybe I can, let me see about doing this. It's a little bit of a sidestep, but I think this can be interesting. So let's make a delme.md, and yeah, okay. So a way that you could do this for Slack, if you wanted it to look nice. Let me show you what I would do if I needed to put nice looking math into Slack. So in VS Code, I'm previewing some MathJax. There's a markup language called MathJax, which is like LaTeX, spelled LaTeX, LaTeX, and a lot of mathematical notation is written in LaTeX. So MathJax is sort of like a pared down version of LaTeX that allows you to do a lot of things. So if I wanted to really write this and have it look nice, I would probably use LaTeX. Del me in this case just means delete me. It's so that when I see it later, I know it doesn't matter, and I'll just delete it. So if I wanted to make something that looks nice, I would maybe say del me, and we'll start I at 1, and we'll go to n, and this is going to be a sub I. Now, is this going to copy well into Slack? I don't think it's going to do a great job, but let's see how it does. If I copy it directly, it looks pretty terrible, but what I can do is just copy this image directly. I'm pretty sure I can just do that and maybe paste that in, right? So that gives me some nice mathematical representation. Yeah, the more you play around with MathJax and LaTeX, the better able you are to represent represent formulas. So let me just as an example, let's take that that binomial PMF and translate this into MathJax. So it's here. That's what it looks like symbolically. If I start writing this out, right, the probability that x is k, so we're on our way already. And then I think this is just choose. Just this, n and k. No, it is not. Okay. Choose. I think I often have to look this one up. Okay. So in that case, you have to look things up. So what I would look for is just MathJax combination. Oh, I see. That's why. N choose. There it is. Okay. With LaTeX, I'm often looking stuff up because I forget things. So there's part of our formula. And then we want to just, this is just p to the k multiplied by 1 minus p to the n minus k. So that's a way that we can write that formula, and of course I can just copy, I can screen capture that and I can paste it in if I want to. There are times possibly where you might paste in the actual formula in LaTeX form. When I see this in LaTeX or in MathJax, I find this very readable, actually. I can read this as what it is without too much trouble. But that's from a lot of practice, a lot of practice writing it. So that's a very brief introduction to MathJax. Okay. So with that, let's think a little bit more about binomial, and let's think about, let's say, binomial type questions. So let me, I set aside the code. Let me just grab all of that and paste it back in. So we had factorial, and combinations, and then we had the binomial PMF. Something you might be wondering is, well, we've got the binomial PMF, but we could probably use a binomial CDF, and a way that I can write the binomial CDF is, let's think about n, and we're going to think about the high value of k and the probability, which we'll say is 0.5. For the binomial CDF, I'm just going to make a cumulative function, and I think that's fine. I think that's you know, even when we represent this mathematically, that's what we're doing. And so here we've got the cumulative distribution function, and you know, if we look at this, we have the summation here, right? The summation, and instead of n choose k, we're doing n choose I, and we're summing the results of this whole expression up to k. So starting at 0, going up to k. And that's something that we can just, you know, we can just code explicitly. We just have an accumulator, some accumulator, and we say for k in range high k, right, including high k, then we're going to accumulate across this. We're going to say accumulate plus gets the binomial PMF of n, k, and p. We have n, k, and p, and then we can just return the accumulator. And so if we do this, we can answer certain types of questions, right? We can answer the question, what is the probability of getting 4 heads in, getting 4 or less heads in 10 coin flips? We can answer that very easily if we have this binomial CDF problem, or function. So this is n of 10, high k of 4, and we should see that probability. It should be a little bit less than 0.5. Oops. So 0.376. Now, what is the probability of getting 5 or less heads in 10 flips? 0.623. So that's 0 heads, 1 heads, 2, 3, 4, 5. Okay. So those are the main things that we think about in general with these discrete distributions, right? We think about the PMF and the CDF, and we start answering certain kinds of questions. Those questions can be fairly easy to make up if you understand the problem, and if you understand what a binomial distribution is. So let's think about, well, let's see. There's a question, I put n minus k in curly braces. Will you get the same LaTeX output with parentheses? No. Yeah, it's with that markdown, with that MathJax, I put them in curly braces. That just makes sure that they exist in the same level. What does high k stand for? That's up into the value that we're trying to get the distribution. Get the probability. So high k is like, you know, if we're looking at the probability of getting 4 or less flips, then high k is going to be 4, because we want to consider k of 0, k of 1, k of 2, k of 3, and k of 4. So that's 5 out of those 10 values. So let's, I'm going to write a couple questions, sort of binomial style questions. And what you'll start finding out, so I wrote a coin flip problem. That was pretty straightforward, right? That was pretty easy. Let's think about a different kind of problem. Let's say a different story. So sitting on a dock, watching boats go by, let's just say you are sitting on a dock. You are sitting on a dock watching boats go by. The probability of seeing a yacht is, you know, when of seeing a yacht when you see a boat, right? So you see a boat and you're like, that's a yacht. The probability of that is, you know, let's say 0.05. What is the probability that when observing 50 boats, you see 5 yachts? Okay, so exactly 5 yachts. This is a binomial PMF problem. And with that, we can grab this binomial PMF and we can sort of fill it in, right? So n is going to be 50, right? There are 50 experiments, there are 50 trials, and 5 is going to be the you know, the target. That's your k value, where you're asking what is the probability of seeing k yachts, and then the probability of seeing any given yacht is 0.05. Any given boat as a yacht is 0.05. So let's run that. The probability is, you know, roughly 6.6%, or 0.066. And but the trick here is seeing this as being binomial. And so what I'm going to do is take this question and adapt it. Okay? So you are sitting, how about you are standing, I'll just change a few words. You are standing on a busy street, watching cars go by. The probability of seeing a, oh gosh, I don't know, Carmen Gia, right? Is that how you spell it? In your town is 0.05. I don't know why I made that a question up there, but what is the probability that when observing 50 cars, you see 5 Carmen Gias? Obviously, this is going to be the same result, right? This is going to, you're going to plug in the same numbers, you're going to get the same answer. And so after I set up this story, maybe I change these numbers. So maybe it's 0.13. And maybe instead of 50 cars, it's 25 cars, right? And you see 3 Carmen Gias. Maybe maybe I even make this a little trickier and I say, instead of the probability of seeing a Carmen Gia, I say, you know, 13 out of 100 cars in your town are Carmen Gias, right? So 13 out of 100 cars in your town are Carmen Gias. I have no idea if this is the right way to spell this. What is the probability that when observing 25 cars you see 3 Carmen Gias? Well, we're gonna make some assumptions here that everyone's driving their Carmen Gias around and all the time. You know, we're gonna make some assumptions, but at the end of this, we're just gonna plug some numbers in, right? That's gonna be what we get out of this. So what is our n? Our n is going to be 25. There are 25 cars that we are considering. Our k is 3. We want to know the probability of seeing 3. And our probability of seeing any given car as a Carmen Gia is 0.13. So that is going to get us an answer of 0.236. So my point being here that, yeah, we can think about this in terms of coin flips, but the phenomenon, we can abstract that away and we can write other specific problems. And the trick starts coming down to whether or not you see these as binomial problems. After you start seeing these as binomial problems, and I honestly think the best way to do that is by writing new problems yourself. After you start seeing these as binomial problems, what you can start doing is you can start learning the other distributions. Let's say. Oh, I'm sorry. Here we go. You can start learning the other distributions and purposefully distinguishing between, say, a binomial problem and a Poisson problem, or a binomial problem and a geometric problem, because they are different. They answer different questions, and so write your own problems. Also, practice these a lot. These sort of textbook problems, because they're going to help you in the technical interview, and also in general, you'll want to be able to recognize the common distributions. And I would say the common distributions that we want you to know are binomial, let's say uniform, Bernoulli, binomial, Poisson, geometric, normal, exponential. There are other distributions out there, a lot of them, and they all represent different phenomena. And if you want a tour of them, of what they look like, I think, let me see if I can track this down really fast. There's a great little snippet of code somewhere. Oh, you know what? I thought I had it on the Premium Prep landing site, but I don't. So I'm gonna just Google Stack Overflow. What do all the distributions in SciPy stats look like? So SciPy stats is your, one of your major statistics libraries for Python. There's also stats models. There's a few of them. So this is going to show us all of the. So this is a normal distribution where it's been put into a histogram of 32 bins. And then, I think all the code to generate this is down at the bottom. But these are all different distributions. Notice that there are a lot of them. So we've got the Cauchy distribution, Weibull distribution. Here's the code that will actually generate all these if you have, SciPy installed. Which you will if you're using Anaconda. There are a lot of distributions, right? Here's a uniform distribution. Let's see if this has Dirichlet. Oh, it does not. I thought maybe it would have the Dirichlet distribution, but it doesn't. But yeah, a T distribution, which comes up in hypothesis testing. Some of these are going to be more important, more commonly used than other distributions, just to be really clear. And depending on what domain you're in, right, you might be thinking a lot about Pareto. You might be thinking a lot about that. You might be doing a lot with the normal distribution. In fact, you likely will be. Normal distribution comes up quite a bit, but there are a lot of distributions, and we want to prime you in a few of them, so that later when you encounter other distributions, you have a general ability to kind of take them in and understand what their purpose is or how you'll be utilizing them. Okay. So let's just jump back over to this. What in these statements clues me in that these are binomial? Okay. Well, I have a probability here. 13 out of 100 cars in your town are Carminguias. Okay. That's, I can interpret that as a probability. If I see a random car, Bernoulli trial, sort of, what's the probability that it's a Carminguia? Well, it's 0.13. What's the probability that when observing 25 cars, you see 3 Carminguias? I see a number of trials here, observing 25, right? There are 25 trials, and I'm wondering what the probability is that 3 of them are this specific thing. So, if we wanted to change this, if I wanted to abstract this out to sort of a core idea of the binomial distribution, I might think of it in terms of coin flips, right? So, I'm flipping a coin, an unfair coin that has a probability of getting heads of 0.13. What's the probability that when I flip the coin 25 times, I see 3 heads? To me, that's the same question. So that's how I would see these as binomial, is I root it into some basic idea. But by the time you see enough of these, it's easier to do that. You're like, well, is that a binomial problem? And you think about it for a second, you're like, yeah, I think that is. Or no, there's something I'm missing. I might be missing K. I might not be thinking of this in terms of the different ways that I can get successes over a series of trials. There's a question, is the motivation for creating distributions in Python in order to later plot them in visual graphs? I will say this. This is a nice reference. Like, these plots look fine, and there might be something else I want to plot that, I might snipe some of this code, possibly, but at the end of the day, like, a good reason to know distributions is in order to, if you're observing a phenomenon, kind of a phenomenon in the wild, can you tie it back to a distribution, a known distribution? Because if you can, it makes, if you can tie that back to a known distribution, it makes, predicting an outcome much easier. You can get a clear probability on an outcome if you're working from a known distribution. The other thing that comes up a lot is there are algorithms that take guesses. Okay, so you might be observing something, you might be observing some data. The algorithm is going to guess. It'll usually guess out of a known distribution, where that known distribution is assumed to look something like the phenomenon itself. And so there's a distribution called the Dirichlet distribution. It's very sparse, and it's sometimes used to take guesses about words and topics in text, because you might have a document that has like a little bit of a couple topics and not much of any of the other topics, or has representation of some words in a vocabulary, but that only some words, right? So you might guess as to whether or not this word is tied to a specific topic, and you might guess as to whether this topic is tied to a specific document. And when you do that, you want to do that with some sparsity. So distributions can give you a place to guess from, and then you tune those guesses through some kind of Markov chain approach, right? Like some kind of compare the results approach, and you keep updating the results of the observation, if that makes sense. So there are these kind of random approaches where you update your belief, and you start to settle on, if your belief doesn't change too much with your next observation, you start settling on a specific probability potentially, or a specific outcome, or prediction, or grouping in terms of unsupervised learning, where you're not necessarily trying to guess an outcome, but you're trying to discern relationships amongst pieces of data. Okay, so that's we're kind of off in some other space now, but one thing I will say, Stack Overflow is pretty amazing. So if you haven't played around on there, or looked for help on there, and when I say looked for help, what I What I really mean is, you Google something and you end up on Stack Overflow because somebody has essentially answered a similar question to yours. You probably want to get into Stack Overflow and just see what's there. Speaking of which, if you are interested in learning MathJax, and at some point you will need to learn MathJax, there is a reference page on Stack Exchange, which is directly related to Stack Overflow. Not sure, fine, except cookies, whatever. There's a single page on this which is just about the best MathJax reference guide that I've seen. There's a question, what use cases do you like Markov chains for? When I've coded out latent Dirichlet allocation, that algorithm, I coded it from a Markov chain approach, and I coded it from a, another approach that I can't remember the name. But, that said, Markov chains have a lot of applications, really, and it's worth just opening up the Wikipedia article on it. There are a ton of applications. in fact, some of the things that we do in Premium Prep take a bit of a Markov chain approach. Not yet, but we will. I'm not going to point it out when we get to it, but because we're sort of building these underlying ideas. But I definitely recommend reading up on, just reading through the Wikipedia page. It's not, I think it's fairly accessible, but it shows up as a strategy. It shows up a lot, and so kind of narrowing it down is. Oh, cool. Yeah. Yes, so definitely one Markov chain application is, writing poetry based on Gutenberg project books. And a lot of things fall under the category of Markov chains, and you might not realize it. So I think looking at sort of a general reference on it is good. Reading through Wikipedia, I think, on it is really good. So that's about it for study hall today. A number of you I'll see in class tonight. And the next study hall will be on Friday. I think, let me see, preemptively. So in general, I'm going to be doing the Wednesday study halls, and Clark will be doing Mondays and Fridays. We might switch off now and then. I think it's likely that next week, because of the upcoming holiday, we won't have Friday study hall, but this week we will. So, and it'll be regular, after that. We probably won't have one on Monday the 4th either. Monday the 5th, since that's a national holiday. All right. Thanks so much, everybody, and have a wonderful day.